Before I introduce Professor Gross and his lecture, may I first call upon the President of Chiang Mai University, Professor Pongsak Angkasit, to formally start this afternoon proceeding with his opening address, please.
Good afternoon. Professor Prof, Mr. Chiang is representative from International Peace Foundation, Deans of the Faculty of Science, academic colleague, distinguished guests, ladies and gentlemen. On behalf of Chiang Mai University, I would like to extend our warm welcome all of you to the second of this new series of Nobel Prize Laureate Science Lecture. We are very proud and privileged to host this lecture series, which will provide us with a unique opportunity to be able to listen and learn from some of the world's most distinguished scientists. Professor David Cross from the Institute of Theoretical Physics, University of California, was the Nobel Prize Laureate for Physics in the year 2004. And we are deeply honored to have him with us here today to receive the ultimate accolade with the Nobel Prize recognition, not only academic excellence in research, but also the benefit that the research brings to society as a whole. This is certainly true in the case of Professor Cross' work, and his lecture today should serve us as an inspiration to us all. I would like to take this opportunity to express our gratitude to the International Peace Foundation and the Thai Area International, without whose support today's lecture would not be possible. Also to thank Dean and his colleagues in the Faculty of Science for the time and energy to have them contribute to organize and hosting this event. Also, David Cross, our most sincere thanks and appreciation to you for honoring us with your presence, and I trust that the memory of you take with you on this lecture and our city will hasten your return in the not too distant future. Thank you very much.
Thank you very much, the President of Chiang Mai University. May I now invite the President once again to present a token of appreciation to Professor Gross and Mrs. Gross and Mr. Heckman. You all be in the front to take the group photo, please. Sorry. One more time. Thank you very much. And thank you, Professor Pongsak, the President of Chiang Mai University, for the opening address. As mentioned earlier, this new series of Nobel laureate science lectures is hosted through the International Peace Foundation. Therefore, I call upon Mr. Yanis Hegman, the representative of the International Peace Foundation, to introduce this series Nobel laureate science lectures.
And welcome to the third ASEAN series of Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation under the common patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including some of the country's major universities. Having started in November 2009, Bridges will be continuously held in Thailand, Cambodia and the Philippines until April 2010, involving the participation of Nobel laureates and other eminent keynote speakers. The third ASEAN series of Bridges is an independent contribution to the Decade for a Culture of Peace and Non-Violence, initiated and promoted by the United Nations General Assembly. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, culture, politics, economy, religion, the media and the youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. And therefore, the foundation itself is a bridge and a facilitator between different language groups in our divided societies. Where politicians speak another language than artists, and business and religious leaders another one than scientists. In a highly interdependent world, problems cannot only be solved by one of these language groups, but by finding ways of working together. After the success of Bridges in Thailand, the Philippines and Malaysia, the International Peace Foundation has now been invited by other ASEAN countries to build further bridges towards peace and international understanding by expanding its program in Southeast Asia to stimulate the intellectual, scientific and cultural exchange in the region. The topics of the ongoing events deal with the overall theme of building a culture of peace and development in a globalized world, and with a wide range of issues in the field of politics, economy, science, culture and the media. And they especially highlight the challenges of both globalization and regionalism and its impact on development and international cooperation. The aim of Bridges is to facilitate and strengthen dialogue and communication between societies in Southeast Asia, with their multiple cultures and faiths, as well as with peoples in other parts of the world, to promote understanding and trust. The events aim at building bridges with the local universities and other institutions in Southeast Asia to establish long-term relationships with Nobel laureates in all fields, which may result in common research programs and other forms of collaboration. By enhancing science, technology and education as a basis for peace and development, the events may lead to better cooperation for the advancement of peace, freedom and security in the region, with the active involvement of the young generation, ASEAN's key to the future. This is why Bridges is not designed as a one-time event, but as a continuing process of synergies, to make the series of events a sustainable success for Thailand, the Philippines, Cambodia, and Southeast Asia as a whole. We are very grateful to Chiang University, as well as to our other partners and sponsors who have enabled us to make the idea of Bridges a reality. And I would like to say thank you to everyone present here today for taking part in this program. May it help us to facilitate a new culture of peace through dialogue, transcending its definition as merely the absence of war or armed conflict, into a new understanding of what the basis for peace can be, education. In this spirit, we welcome today Professor David Gross, the 2004 Nobel Laureate for Physics, who again has agreed to come to Thailand to support the events. And we all look forward to his keynote speech and to his important contribution to build bridges. A warm welcome, Professor David Gross.
This afternoon's speaker, Professor David J. Gross, received the Nobel Prize for Physics in 2004 for his great discovery of the force that binds radical insight and atomic nucleus. This phenomenon leads to a whole new physical theory and enables scientists to complete the standard model of particle physics, which describes the fundamental particles in nature and how they interact with one another. A formal introduction of Professor Prof's lifetime achievement and his great discovery on this phenomenon will be addressed by Professor Emeritus Thong, the Director of Thailand Center of Excellence in Physics. Please welcome Professor Emeritus Thong.
สวัสดีปีใหม่ครับท่าน Happy New Year Everybody
I say again สวัสดีปีใหม่ครับทุกท่าน and Happy New Year Everybody looks serious it is beautiful Monday in Chiang Mai and today I have great pleasure in introducing to you one of the most admired and brilliant physicists of our time. And Professor Gross, he was born in Washington, D.C. on February 1941, right in the middle of the Second World War. When he was about 12 years old, he went with his parents to live in Jerusalem, Israel, the newly founded state of Israel. And he went to school there. And as early as 13 years old, Professor Gross was attracted to physics and mathematics and determined to become a theoretical physicist, I believe. At the time, he said that he had no idea what that meant. I believe nowadays many of us don't know what a theoretical physicist is doing either. He will tell us today about what theoretical physics is all about. Well, he received his BSc in physics and mathematics from Hebrew University in Jerusalem, and went to do his PhD at the University of California, Berkeley in the 60s. So he was one of the 60s generation. So you can, everybody who interested in the life in the 60s could ask him later on. He received his PhD there in 1966, and then went on to do his postdoctoral work at Harvard University. Here, he was nominated to the Harvard Society of Fellows, which is an institute that gives a sort of appoints a fellow each year, with only one condition, that once a week you have to dine with the senior fellow. So here at Harvard, great physicists, some of them later on become a Nobel laureate, such as
Sheldon Chiang, and others. And here he started to do some work that led to the discovery of new phenomena. He stayed at Harvard for 3 years, and then he was offered a job at Princeton in 1969, when he took an offer to become assistant professor. And very, very quick, early in 1971, he was become a tenured professor then, for a very, very quick career. Here at Princeton, he has 2 very, very top graduate students. His name at that time were Frank Wissett and Edward Witten. Now, Professor Wissett now is at MIT, and Chiang Nobel Prize with him. And Professor Witten is now at Princeton University, and one of the most cited physicists of our time, the work of Professor Witten. In 1973, he and Professor Wissett published a paper in the Physical Review Letter, because this is the top journal in physics as we regard physics, in volume 30, the seminal paper about his discovery that led him to the Nobel Prize. Professor Gross, in 1996, became the director of the Institute for Theoretical Physics at UC in Santa Barbara, and now is known as the Carey Institute. It's the top institute, the world top institute in theoretical physics. Professor Gross received many honors and awards, including that I would like to mention is the J.J. Sakurai Prize, given by the American Physics Society in 1986. And then in 1988, he received the Dirac Medal of the ICTP for work on theoretical physics. And also in the year 2000, he received the Oscar Klein Medal at Stockholm University. And of course, the highest honor is the Nobel Prize in Physics in the year 2004. And today, Professor Gross will give us talk about science and human development. And it is a pleasure to introduce to you now Professor Gross. Please welcome.
you hear me? Can you hear me? Can you hear me now? Yes. Savadi Bimai. It's really a pleasure to be here in Thailand again and in Chiang Mai for the first time. We arrived, what is today? Today is Monday. We arrived Saturday, and we've had a lovely time in this beautiful, beautiful city. We've met some lovely people, and today I had a tour of the physics department and the new Center of Excellence, of which I'm very impressed. It really has been a great pleasure, and I would like to thank my hosts, of course the Bridges Foundation, and all of you for coming to hear my lecture. I would like to apologize to my scientist friends in the audience, because my lecture will be a rather general lecture. So those of you who are not in physics, you don't have to be scared. But for those of you who are in physics, I hope that after the lecture you'll have time to ask me about string theory or quantum computing or whatever you want, including life in Berkeley in the 60s. So, is this working now? So, my talk is on science. What it has brought us, what it will bring us, and some general speculation about science and what we will learn, and about the human condition in general. Mostly I'm going to talk about, in a very general sense, the gifts of science. What science has brought us. And the first of the gifts that I will discuss is just the scientific method alone. For even without the fruits of knowledge that science brings us and their application to technology, the greatest gift that science brings us is a new way of thinking. And this new way of thinking, which the scientific method, is of course extremely powerful in science, but it's a powerful and important way of thinking that could be as useful and is as useful in all areas of human study and all areas of human discourse. Then I'll briefly discuss the knowledge of nature that science provides. This is its most obvious gift, understanding how nature works. And I'll give some examples from both physics, astronomy, biology, which have totally changed our understanding of nature in a very short time. And then, of course, science. In science, we apply that knowledge that we have gained to control nature, to try to manipulate and use nature to our advantage. So the third topic will be the control of nature, application of science, technology, which has brought us so many good things and so many bad things. And in responding to those bad things, to the problems we face, some of which are consequences of our ability to even change the face of our planet, I'll remark on one of the other gifts of science that is not widely recognized, and that is its international character. And I'll speculate on how that might serve as a model for a growing internationalism that we truly need to solve some of the planet's problems. And as a scientist, I will end with questions because that is the driving force of science. And as a theoretical physicist, of course, my business is to make predictions. So I'll make some predictions. Let me start with a scientific method. This is a new way of thinking. It was only invented about 400 years ago, whereas we humans have been talking for maybe 100,000 years or more. And it's proved to be very powerful, and it's based primarily on the idea that understanding, knowing, is best attained by every once in a while, or continuously, subjecting our ideas to observation and experiment. That the only authority for truth in the end is agreement with nature through observation and experiment, and not on the basis of power or religious faith and dogma. So the first time I met the Dalai Lama, who I've met a few times, we had a very interesting discussion about science and religion. And I asked him, is there anything that science is currently exploring? Any answer that we might find that would be in conflict, would cause you problems with Buddhism as you practice it? And he said, nothing. If scientists discover by the scientific method a phenomenon which they understand and is tested on the basis of observation and experiment, and our writings say otherwise, we must agree with science. I was very impressed by the Dalai Lama. And scientists know also that their truth, what they learn, their theories that are tested, are not going to last forever. They are always provisional. They're very likely to be changed. And we continue to subject our theories to quantitative test and improvement. We look for nature to tell us that our theories are wrong. Then we've learned something very important, and we try to construct a better theory. It's not that our theories are going to be lost. Newton's theory of mechanics has been replaced by quantum mechanics and by relativistic mechanics, but it is still an extremely good approximation to the better theories. Theories in physics don't die, they just become approximations. So we don't believe in absolute truth in the sense that our theories are not going to be improved in the future. And the final part of the scientific method is that we scientists feel the obligation to make our results available to all. In society, in places, in countries where scientific results are not made available to all, or if because of commercial interests scientific results are not made available openly to science suffers. We have learned that science itself flourishes only when you have openness, when we publish our results in journals and everyone can read them, or put them on the internet and they're available to everyone, anywhere, immediately. I believe that this method that has been honed and improved over the last 400 years is in of itself is of great social value to humanity. And it has implications for how we live and how we interact with one another. For a healthy scientific culture truly requires an open society. Scientists among themselves are a very open society, and anything that stops discussion, stifles debate, promotes authority is bad for science. Science promotes tolerance. We might be wrong. Any idea I have might be wrong. So I must tolerate other people's ideas, even if they're different than mine. And that is a very important human value. And in effect, science promotes democracy. Because we all, as scientists, we all understand that everyone is equal in science. I can give a lecture describing my theory, and a bright young student with no credentials can get up and say, "But you're wrong." And he might be right. So these are values of the scientific approach, which we've adopted maybe only because they're good for science, but they're also good for tolerance, for democracy, for openness, transparency. But of course, the main goal of science is to provide knowledge of nature. We human beings are programmed biologically for our survival to construct models, explanations of the world. And with the scientific method, we've learned to do that very well. And I'll give just a very quick history of physics, astrophysics, cosmology, and biology. Physics, of course, is the oldest science, the queen of sciences, we physicists say. It's been going strong for 400 years and is an amazingly successful enterprise. 400 years is not a long time. That's the life of 6 people, one after another. So just 6 lifetimes ago, Galileo and Newton started the scientific approach to physics. And now we have a theory that seems to explain just about everything until we get down to the very, very short distances. Astrophysics, people have been doing forever. Astronomy, looking at the stars, trying to understand what the universe is made of. In the last 100 years, we have gone from thinking that we lived in a static Milky Way and that was the universe, to understanding the whole history of the universe from almost its beginning till now. In biology is perhaps the youngest of the sciences and has made enormous strides, but still it's in its infancy. So let's start with physics. And I've tried to summarize in a few sentences what we've learned over 400 years. At the beginning, Galileo Newton discovered the basic laws of motion that govern motion of bodies and the symmetries of nature that we've learned more and more are the basis of that dictate the forces that act on bodies and make them move. We have unveiled the structure of matter, the underlying atomic structure of matter, whose atoms form the constituents of all the matter we see naturally around us. And we've learned that they are governed by strange laws of quantum mechanics. the last 100 years, we have constructed a comprehensive quantitative theory of both atomic and nuclear forces, identified the basic constituents of matter, and now we are engaged in an ambitious attempt to try to unify all these forces together. We're far from that goal, but we're working on it. And it really all started, as I said, only 6 lifetimes ago with Galileo, who, aside from being a great experimentalist and developing the telescope and other experimental tools, was also a theoretical physicist. And he understood the first time that the language of science is mathematics, which is why it's often so hard to explain physics to people who don't know mathematics. Mathematics, our most highly developed form of language, is necessary to understand nature. And the more we learn about nature at its most fundamental level, the more we discover a beautiful mathematical structure behind it. Newton used Galileo's insights and the mathematics he developed and his intuition to construct a universal theory for the first time that both explained apples and planets, subject to the same law of gravity, and a theory strong and powerful enough that he could predict and calculate with precision the motion of the planets. And Newton's theory was so powerful that it set the stage for all of modern science. This goal of constructing a quantitative explanation of all phenomena continually subjected to experimental test. And this was all done just in the first 100 years. In the 19th century, Maxwell unified the phenomena of magnetism and electricity and realized that light was a wave in the electromagnetic field that described electricity. And all of the phenomena of light and electricity and magnetism could be summarized in a set of beautiful equations that you can put on one t-shirt. This was also the century of the Industrial Revolution, where we learned to construct machines and transform heat into mechanical work. We understood heat and energy and entropy. And this is one of the heroes of that development, Ludwig Boltzmann, who understood what entropy was really about. And finally, in the 20th century, we completed the atomic theory of matter, starting with the realization that all ordinary matter is made of atoms. Atoms have a structure. They're not just little hard dots. They have a structure. They consist of a very small nucleus and an electron cloud whirling around that determines the structure of individual atoms and molecules. So atoms, we understood, are electrons revolving around nuclei, and in order to understand their structure, one had to invent quantum mechanics, a whole new way of looking at the world, replacing classical mechanics. Here are some of the heroes that did this great development in the beginning of the 20th century: Planck and Einstein, Schrödinger, Bohr, Heisenberg and Dirac, and of course Rutherford, who discovered the nucleus. And as it has turned out, over the century and continuing today, we understand that the collective behavior of atoms is responsible for all the properties and phases and behavior of matter, including all of chemistry. And supposedly all of biology is determined by just these atoms interacting with each other. The basic equations that describe this could also be written on one t-shirt. That's not to say we understand how biochemistry and biology work based on that t-shirt, but in principle, we think that is the case. Also, in the 20th century, we learned that space-time is more complicated than we thought. It's dynamical, said Einstein, and mass and energy curve space, giving rise to gravity. And finally, in the last half of the 20th century, my generation, we completed the so-called standard model, or the standard theory of particles. We identified all of the elementary particles of nature that constitute ordinary matter, and they consist of quarks inside the nucleus, electrons, a cloud around the nucleus, accompanied by neutrinos, very light particles. We discovered 3 families of such particles, and most importantly, we identified the 3 basic forces of nature in addition to gravity. Force of electromagnetism was known for quite a while, but in the 20th century we understood the force that acts inside the nucleus, the strong and weak nuclear forces. And I'll say a word about the strong nuclear force because that's the one that we figured out. So, the nuclear force. This was a very hard force to understand since it operated inside this teeny little nucleus that is buried inside the atom and hard to peer within. And as we began to look inside the nucleus, experiments showed, just as I was leaving graduate school, that the proton looked as if it were made out of freely moving point-like particles called quarks. Because you couldn't pull the quarks out of the proton. You hit the protons hard, the quarks never came out. But if they're moving freely, what's stopping them from coming out? And that eventually led us to discovering a new phenomena, which led us to the theory behind this strange behavior, and turned out to be the theory of the nuclear force. And I'll spend a bit on the physics here because it's interesting. It all depends on the properties of the vacuum. Now, the vacuum, you might think, is pretty boring. And that's true in the classical world. The classical vacuum is empty. You know, if you take everything out of this room, all the people and the air and the rug, the furniture, and you're left with nothing, that's the vacuum, right? Boring. This is a picture of the classical vacuum. Or here's a better picture of the classical vacuum. I like to tell my friends that, you know, what particle physicists do most of their life is study nothing. Study the vacuum. In order to understand particles and their behavior, we have to first understand nothing, the vacuum. Now, the reason the vacuum is much more interesting than this picture is that in quantum mechanics, nothing can be this simple because of the uncertainty principle. Because let's say I really want to study the vacuum, then I probe it. I hit it with a photon, a quanta of light. I shine a flashlight on it, like this. And if I hit it, I disturb it. Now the vacuum is the arena, space-time, the arena in which the fields of electricity and magnetism, the electromagnetic fields and other fields live. And when I observe them, I give them a little kick. They fluctuate. Let me show you a picture, an illustration of what the vacuum really looks like. And I can do this because I'm a theorist, so I can calculate in a good theory what the vacuum really looks like at the nuclear scale, using QCD, of course. This is a picture of the quantum vacuum, which will be full of fluctuating fields. These are fields like the electromagnetic field, but these are the fields that transmit the strong nuclear force. And here it is. This is a calculation done using QCD, or theory of the strong interactions, put on a lattice, discretized, massive computer calculation of fluctuations in the fields that live in the vacuum on the scale of the nucleus. This is about the size of the proton. Here. You don't see that because you can't resolve distances that small, 10 to the minus 13 centimeters. But it's there. The vacuum is a very interesting place. It can have interesting dynamics. And it is the property of the vacuum in a theory like quantum chromodynamics that gives rise to the phenomena that we discovered that led to that theory. The phenomena that if you take quarks and you put them very close together, the force between them is very weak. And the closer they are together, the weaker the force is. That's the phenomena of asymptotic freedom. Which also explains why you can't take the quarks out of the proton, because when you pull them apart, the force gets stronger. And the quarks are confined, held together permanently inside the proton. That's confinement. Well, that was a very nice discovery, and it was only true in one kind of theory. So it led us to a theory later called quantum chromodynamics. It's a theory like electricity and magnetism, where the quarks have a charge, except there are more charges than just one electric charge. There are 3 charges. And so the theory is richer, more complicated, more interesting. And by now it's understood that this theory really works with great precision and describes the nuclear force and the properties of the proton, the neutron, and all the particles you can create in energetic collisions between protons. We can now calculate the mass of the proton and the neutron and the other nuclear particles. Well, that's what led to this. That's the King of Sweden. When you get a Nobel Prize, you get a check, which he's giving me here. You also get a certificate, which has a beautiful picture illustrated by a Swedish artist. And you see what he drew here was a proton with 3 quarks, which can't get out. In fact, they made a poster for the Nobel Prize that shows these 3 quarks trying to escape from the proton, but frustrated because the force is getting stronger and stronger and holding them back. It's a very pretty cartoon, but they got it wrong. Here they have these springs, these forces acting on a triangle like this. Here's a picture of what actually happens, according to the calculations, when you try to pull the quarks out of a proton. You see that you form the field lines form this triad, also preventing the quarks from getting out. This again is a massive computer calculation in QCD. Okay, enough with physics. Let's turn to second area where we've made rapid advances, cosmology. There it is amazing how rapid things have changed. In 1 century, 100 years, we've learned that the universe is enormous, and our sun is only one of 100 billion stars in the Milky Way. But the Milky Way is not the universe. There are 100 billion galaxies in the universe at the moment. And we learned that the universe is expanding like a balloon that you blow up, the surface of a balloon, expanding with almost a constant rate of expansion. And we learned that that expansion began about 13.7 billion years ago from some very hot state, which we call whimsically the Big Bang. We've expanded our horizons from the size from the Earth to the solar system, to the galaxy, and to the universe, the visible universe as a whole, which is about 10 billion light years, the distance light travels in a year across. This is a picture of the universe as a whole, which shows very little structure. And we understand roughly, to a good extent, how this universe developed from a very, very small region of space. We understand most of the history of the universe. From some kind of beginning, a very small region of space, we believe, expanded very rapidly, then settled down. We have a picture of the universe at that close to the beginning, 200,000 years after the beginning. This is what it looked like. This is a picture of an almost uniform gas of light that when atoms, the universe expanded, it cooled, atoms formed out of electrons and nuclei. The atoms are neutral, the light streams through, and this is what we see 13.5 billion years later, that light hitting our eyes. And that light tells us that back then, the universe consisted of this gas of atoms and light, which was almost completely uniform, and the variations in color here, blown up by a factor of 10,000, show the little variations of density in that almost uniform ball of gas. But gravity attracts particles together, and regions that are more dense get pulled together. Regions that are less dense don't. Structure begins to form, and we now can follow that emergence of structure through the formation of stars to galaxies, planets, and we're about here. And most recently, we've learned that this sort of constant expansion of the size of the universe is actually accelerating due to something called dark energy and might continue to accelerate forever. All of this history we've deduced from almost nothing, no understanding, in 100 years. The biggest mystery remains the beginning, the Big Bang, where still all of our equations break down. And now, a good part of cosmology and astrophysics, and certainly the kind of physics I do now, string theory, would love to try to explain the Big Bang itself. That's the biggest unknown that is left. That and the question about what is going to happen in the future. Will the universe expand, indeed, in an accelerated way forever? But most of the history, back to the first billionth of a billionth of a billionth of a billionth of a second, we understand. It's quite remarkable, just 100 years. Finally, a word about the youngest of the sciences, in many ways, biology, which we're celebrating 150 years for this year, last year, of Darwin's publication of The Origin of Species. So over those 150 years, we have learned an incredible amount. We learned that life emerged over 3 billion years ago and was shaped by natural selection and random mutations. We have located and deciphered the genetic code, outlined the basic mechanism of living cells, and discovered the cause of disease. And finally, located the source of consciousness and emotion in the brain, and have started to explore its mysteries. All of this just in 150 years, 2 lifetimes. And 150 years, indeed, is since the publication of the fundamental theory of life, namely natural selection. International companies, which are powerful social economic players, are already international. But why stop at 100 years? It is very much fun to think on a human scale. A human scale is 100,000 years, 10,000 years. Our species has been around for 1 million years. Maybe Homo sapiens talking, creating 100,000 years. What about a very short time compared to that, 1,000 years? Remember, all of science, modern science, is only 400 years old. The Industrial Revolution, less than 150, about 150. What will be in 1,000 years? Of course, none of us can imagine. But some of the things that will change due to our science and will be big problems as well in the future will be things like a much increased lifespan. We've doubled the lifespan in 100 years, 200 years, with just better nutrition and better medicine. But now that we can control the human genome, we will have, I have no doubt, a much larger lifespan, 200 to 400 years. We also face the possibility, the likelihood of changing the genetic code, of hurrying up mutation and evolution by our interfering with our own DNA. That might be good. It might lead to, for example, a longer life. But it's bound also to lead to speciation. What happens to all species, successful species that don't go extinct, is that they divide up into many species. We too are probably just a branch along the way in the evolution of our species. And we might evolve into more than one species, which could cause big social problems. And finally, if we survive on the order of 1,000 to 10,000 years, we will start, or life on Earth, our successors, will start populating the galaxy. It's an easy calculation to realize that if you can survive, if we could survive about 1,000, 10,000 years, we could populate the whole galaxy in a few million years. We would not send people to other stars, other planets, which we're beginning to explore from afar. We would send information, robots with the information necessary to reconstruct from local materials life. That's all you need. Bits of information that encode the genetic code. And we could do this with micro robots in a way that would explore our immediate vicinity. And once you start an exponential expansion like that, you could rapidly, on the time scale of the galaxy, which is billions of years, very rapidly populate the galaxy. So, with that, I conclude, and I conclude with the prediction, the final prediction, that science will be even more important in tomorrow's world. It will continue to reveal more of nature's secrets, increase our control over its forces, with consequences that are both good and potentially bad. My hope is that the culture of science will inspire us to exploit the good and avoid the bad. Thank you.
For your fascinating lecture. Before I get the question from the audience, let me summarize your lecture in Thai for a few minutes. You can listen to the Thai version of your talk also. จากหัวข้อนะคะ Science and Human Development แปลเป็นภาษาไทยได้ว่าวิทยาศาสตร์และพัฒนาการของมนุษยชาตินะคะโดย Professor Cross ได้พูดเกี่ยวกับกิฟต์หรือของขวัญจากวิทยาศาสตร์5ประการสำคัญนะคะก็คือของขวัญชิ้นแรกก็คือกระบวนการทางวิทยาศาสตร์นะคะต่อมาก็คือความเข้าใจในธรรมชาติหรือองค์ความรู้เกี่ยวกับธรรมชาตินะคะการควบคุมและจัดการธรรมชาติแล้วก็ internationalism หรือลัทธิการอยู่ร่วมกันระหว่างประเทศนะคะแล้วก็ถึงอันสุดท้ายที่เป็นข้อสำคัญก็คือการตั้งคำถามและการคาดการณ์นะคะที่เรามาดูของขวัญชิ้นแรกก่อนเกี่ยวกับเรื่องของกระบวนการทางวิทยาศาสตร์นะคะก็คือเน้นถึงความเข้าใจที่ควรจะได้มาจากการทดสอบความคิดนะคะของเราโดยการสังเกตและทดลองซึ่งความจริงเหล่านี้ซึ่งได้มาจากการสังเกตและการทดลองได้มาจากธรรมชาติโดยไม่ขึ้นอยู่กับอิทธิพลของการเมืองหรือความเชื่อทางศาสนานะคะแล้วก็ทฤษฎีทั้งหมดที่เราเคยเรียนรู้มาสามารถเปลี่ยนแปลงได้และจะต้องผ่านการทดสอบและพัฒนาอย่างต่อเนื่องนะคะและทุกคนควรจะต้องเข้าถึงการค้นพบทางวิทยาศาสตร์ได้นะคะนี้ข้อสำคัญอีกอันหนึ่งที่ทิ้งท้ายไว้สำหรับกระบวนการทางวิทยาศาสตร์ก็คือวัฒนธรรมที่อยู่บนพื้นฐานของวิทยาศาสตร์นะคะต้องการสังคมที่เปิดกว้างในการแลกเปลี่ยนความคิดเห็นนะคะในการอภิปรายนะคะเพื่อที่จะแล้วสิ่งเหล่านี้จะทำให้วิทยาศาสตร์ นำกลับไปสู่สังคมทำให้สังคมมีความอดทนนะคะแล้วก็มีประชาธิปไตยมากยิ่งขึ้นค่ะทีนี้มาดูของขวัญชิ้นที่2ก็คือองค์ความรู้ของธรรมชาติหรือความเข้าใจในธรรมชาตินะคะทางด้านฟิสิกส์นะคะโปรเฟสเซอร์กรอสก็ได้ให้ตัวอย่างสำคัญ3ด้านก็คือฟิสิกส์นะคะแล้วก็จักรวาลวิทยาหรือ cosmology นะคะแล้วก็ชีววิทยาทางด้านฟิสิกส์ก็ได้พูดเกี่ยวกับการค้นพบนะคะทางฟิสิกส์ตั้งแต่เริ่มต้นแต่กาลิเลโอนิวตันแม็กซ์เวลล์แล้วก็บอลต์แมนนะคะแล้วก็พูดถึงว่าเราได้ค้นพบไปจนถึงระดับอะตอมแล้วก็อนุภาคที่เล็กยิ่งกว่านะคะแล้วจนทำให้เกิดความรู้ต่างๆมากมายทั้งทฤษฎีสัมพันธภาพแล้วก็กลศาสตร์ควอนตัมนะคะซึ่งการศึกษาสิ่งที่เล็กกว่าอะตอมนะคะซึ่งเราเรียกว่าอนุภาคมูลฐานเนี่ยทำให้เกิดทฤษฎีเรียกว่าควอนตัมโครโมไดนามิกส์หรือ QCD นะคะส่วนองค์ความรู้อีกอันนึงเกี่ยวกับเรื่องของจักรวาลวิทยาหรือ cosmology นะคะก็Professor Prof ก็ได้พูดถึงว่าในศตวรรษที่ผ่านมาเราได้เรียนรู้เกี่ยวกับจักรวาลมากขึ้นมากมายได้ค้นพบว่าจักรวาลจริงๆแล้วในจักรวาลเนี่ยประกอบไปด้วยกาแล็กซี่หรือดาราจักรอยู่นับแสนล้านกาแล็กซี่นะคะซึ่งจักรวาลเนี่ยได้ถือกำเนิดมาจากปรากฏการณ์บิ๊กแบงเมื่อประมาณนะคะ 14,000 ล้านปีที่แล้วสำหรับทางด้านชีววิทยาซึ่งถือว่าเป็นวิทยาศาสตร์ที่ถือกำเนิดมายังค่อนข้างมีอายุน้อยกว่าฟิสิกส์นะคะแต่ชีววิทยาทำให้เราเรียนรู้สรรพชีวิตว่าได้ถือกำเนิดมาเมื่อ 3,000 ล้านปีก่อนผ่านการวิวัฒนาการนะคะกลายพันธุ์แล้วก็คัดสรรโดยธรรมชาติแล้วเมื่อไม่นานมานี้สิ่งที่เราค้นพบนะคะก็คือเราสามารถรู้ลำดับรหัสพันธุกรรมนะคะทำให้เรารู้ว่าเราอาจจะมาจากพ่อแม่เดียวกันมนุษย์ทั้งโลกแล้วก็เข้าใจกลไกการทำงานของเซลล์สิ่งมีชีวิตนะคะค้นพบสาเหตุของโรคและสิ่งที่สำคัญในการค้นคว้าทางชีววิทยาในปัจจุบันก็คือเราเริ่มที่จะรู้ต้นกำเนิดการรับรู้นะคะแล้วก็กลไกการทำงานของอารมณ์ในสมองส่วนต่างๆของเรานะคะซึ่งเริ่มมีการค้นพบแล้วก็คือเริ่มมีการศึกษาความลี้ลับเหล่านี้มากยิ่งขึ้นนะคะส่วนของขวัญชิ้นที่3นะคะที่เราได้มาจากวิทยาศาสตร์ก็คือความสามารถในการควบคุมแล้วก็จัดการธรรมชาตินะคะวิทยาศาสตร์พื้นฐานนำไปสู่การควบคุมธรรมชาติและเทคโนโลยีนะคะแล้วก็ทำให้เกิดเทคโนโลยีแล้วก็เครื่องมือบางอย่างที่คาดไม่ถึงจากการทดลองทางวิทยาศาสตร์นะคะซึ่งเครื่องมือเหล่านี้ก็มีทั้งคุณอนันต์แล้วก็มีโทษมหันต์ด้วยเช่นกันอย่างเช่นคุณประโยชน์ก็คือการที่เราสามารถเพิ่มสมรรถภาพในการคำนวณเทคโนโลยีในการสื่อสารการขนส่งการแพทย์แต่โทษของเทคโนโลยีเหล่านี้ก็เช่นการสร้างอาวุธนะคะหรือการทำให้เกิดสภาวะโลกร้อนที่เกิดภัยคุกคามในโลกปัจจุบันนะคะแต่โปรเฟสเซอร์กอสก็ได้ให้ทัศนคติว่าวิทยาศาสตร์สามารถช่วยและจะต้องช่วยในภาวะคุกคามเหล่านี้ซึ่งท่านได้ยกตัวอย่างเช่นนาโนเทคโนโลยีที่สามารถนำไปช่วยในการทำให้การใช้พลังงานจากแสงอาทิตย์มีสมรรถภาพมากขึ้นนะคะแต่สิ่งที่เราต้องการมากไปยิ่งกว่าวิทยาศาสตร์นะคะนั่นก็คือระบบการเมืองและเศรษฐกิจนะคะที่ไม่ขึ้นอยู่กับการบริโภคและการเติบโตอย่างไม่รู้จักสิ้นสุดนะคะนั่นคือเราต้องมุ่งสู่การมี world government หรือรัฐบาลนานาชาตินะคะหรือว่ารัฐบาลของโลกนั่นเองนะคะซึ่งนำไปสู่ของขวัญชิ้นที่4ซึ่งพูดเกี่ยวกับ internationalism หรือลัทธิการอยู่ร่วมกันระหว่างประเทศนะคะซึ่ง Professor Gross ได้ให้ทัศนคติว่า internationalism จริงๆแล้วมันมีอยู่ในแวดวงวิทยาศาสตร์นะคะเพราะว่าในแวดวงวิทยาศาสตร์เราไม่ได้คิดปัญหามาจากการเมืองนะคะแต่เราคิดปัญหามาจากธรรมชาตินะคะแล้วก็ทุกคนมีความเท่าเทียมกันในการวิจัยทางด้านวิทยาศาสตร์แล้วก็มีความพยายามร่วมกันนะคะในการที่จะค้นคว้าวิจัยตอบปัญหาจากธรรมชาตินะคะและนอกจากนั้นProfessor Gross ยังได้ยกตัวอย่างนะคะว่าไอน์สไตน์ก็มีมุมมองเช่นเดียวกันเกี่ยวกับแนวคิดของรัฐบาลสหชาติหรือ supranational government นะคะส่วนของขวัญชิ้นที่5นะคะก็คือคำถามและการคาดการณ์นะคะมีประโยคอันนึงนะคะที่น่าสนใจก็คือ the most important product of knowledge is acknowledgement นะคะก็คือการที่เรารู้มากขึ้นทำให้เรารู้ว่าเราจะต้องนิ่งเฉยหรือเพิกเฉยกับอะไรบางอย่างคือมันมีคำถามบางอันที่ไม่ต้องการคำตอบไม่ต้องเสียเวลาไปหาคำตอบนะคะอันนี้ก็เป็นอันหนึ่งนะคะที่ท่านได้ให้แนวคิดไว้ส่วนต่อมานะคะท่านก็ยังได้พูดว่ามันมีคำถามอีกมากมายนะคะที่ต้องการคำตอบนะคะอย่างเช่นจักรวาลเกิดขึ้นได้อย่างไรทฤษฎีสปริงเป็นทางออกหรือไม่นะคะแล้วก็ท่านได้ให้คำคาดการณ์นะคะว่าอีกประมาณ 50-100 ปีจากนี้ไปนะคะว่าคำถามที่เราถามวันนี้น่าจะมีคำตอบนะคะแล้วก็น่าจะเกิดคำถามใหม่ๆนะคะแล้วที่น่าสนใจก็คือในอนาคตต่อไปไม่แน่ 50-100 ปีต่อไปนี้เมื่อเราเรียนรู้ว่าจิตใจนะคะหรือสมองของมนุษย์ทำงานยังไงอาจจะเกิดการเปลี่ยนแปลงที่ว่าศาสตร์พวกสังคมศาสตร์มนุษยศาสตร์หรือว่าเศรษฐศาสตร์นะคะอาจจะกลายเป็นวิทยาศาสตร์ได้นะคะทีนี้ในอนาคตนะคะโปรเฟสเซอร์กรอฟบอกว่าอนาคตของวิทยาศาสตร์จะยิ่งทวีความสำคัญมากยิ่งขึ้นนะคะแล้วท่านก็จบไว้ด้วยว่าในประโยคที่เน้นว่าวัฒนธรรมนะคะบนพื้นฐานวิทยาศาสตร์นะคะจะดลใจให้เราหาในสิ่งที่ควรนะคะหาและทำในสิ่งที่ควรและหลีกเลี่ยงสิ่งที่ไม่ควรหรือสิ่งที่ไม่ดีค่ะอันนี้ก็เป็นบทสรุปคร่าวๆของเลคเชอร์โดย Professor Prof นะคะ Okay, I'm done with the Thai version of your lecture. Just summarize a little bit. So now we are ready to get the question from the audience. Please, anyone have question? If you don't know how to ask your question in English, you can ask in Thai and then I will translate it. ถ้ากลัวจะถามคำถามนะคะเป็นภาษาอังกฤษถามเป็นภาษาไทยก็ได้แล้วเดี๋ยวจะแปลเป็นภาษาอังกฤษให้ท่านโปรเฟสเซอร์ That's the microphone.
ดึงมาเลย
Professor Cross, your lecture is excellent. Listening to your excellent lecture aroused a lot of interest in Christians. Can we take only 2 or 3 questions? I have a lot of questions. First one is a rumor that in year 2000, this is related to electromagnetism. In year 2012, there's a rumor that there will be the change of the field of magnetisms, the world magnetisms, and it will cause the world great destructions. There will be a great flood, great fire, volcano eruptions, whatever, and maybe a lot of millions of people will, somehow lost their lives. A lot of calamities to the world. That's a rumor. I'm not a physics person. Question number. I'd like to hear your comments on this. Let me finish with 2 other questions. Question number 2. Also, another rumor that there will be the fall of the comets that are running on the way of our Earth and it will struck our Earth somehow. And the scientists, US I suppose, is creating a building, the rocket to shoot this fall from the comets. Okay, and whether it will be successful or not, or we will hurt, struck our world and a lot of people will lose their life. And the last one? I'm scared to hear the last one. The third question is, you mentioned that we should have overconsumptions and we avoid using fossil fuel to especially cars in your country, in the US, that you consume so much energy, and other big countries. Can be avoided by using something alternative energy like hydro energy or hydrogen from water and also dry cell manufacturing for car, for printing. That's my question. I'd like to hear your comments and predictions on this. Thank you very much, and I appreciate it a lot. Thank you. 2012. The only thing I know that happened in 2012 is when the Mayan calendar comes to the end of a cycle. So some people say that therefore there will be trouble. But even in Mayan, of course, people don't know too much about that, understand too much of Mayan astronomy or astrology. But I think the cycle just begins again and lasts for 10,000 years, a very long time. So I don't think this. The meteorite, a comet, or hitting the Earth, we're in pretty good shape because we went for millions of years without knowing whether there was anything approaching the Earth. Now we can actually detect them and predict many years ahead of time whether they'll come close to the Earth. So I did read recently of some meteorites that will have a close encounter. That means 40,000 kilometers or more with the Earth, and that the probability of collisions is continually decreasing. But there are lots of people, both in Russia and the United States, who build rockets, who would love to have an excuse to build new rockets. But it's good to have the ability to see these things. I think the ability is good enough now so that if one saw a comet is big, but a large meteorite, one would have enough time to maybe prepare a space vehicle that could change its course. As far as solving the energy problem goes, that's a long-term project. I think eventually it's probably solar power. Hydroelectric has been exploited everywhere in the world, almost to its full capacity. And wind is very useful where there is wind. But the sun is always there, and eventually I think it'll be exploitable at a reasonable cost. The real problem is the next 50 years because we're so dependent on fossil fuels, not just oil, which we've been using up very rapidly, but coal, as you know. And as it turns out, the biggest coal reserves in the world happen to be in the US, China, India, and Russia, which also make the most pollution and CO2 emission. So where I hope a lot of attention should be invested is in figuring out how in an economically reasonable way to use that coal cleanly to remove the CO2 from the emissions. Otherwise, it's hard to imagine that the US, India, China will not use that coal. It's there, and it's cheap, and it's enormous amounts of it. It's very dangerous. So we have to pressure our governments and other governments to move towards clean use of fossil fuels that we will still use and developing renewable, clean energy sources. One of them is nuclear power. A part of the solution over the next few hundred years is nuclear power, which is clean. The only danger there is proliferation and the use. But that's a political problem and should be solved anyway. And nuclear energy is something I think should be as China is doing, and the US is beginning to think about doing, and Europe is starting to do again, nuclear power can be a very clean and economically viable way of producing energy.
I'm the student of Chiang Mai University. Chiang Mai University. I want to know your view about the unified field theory. Do you think that the theory will be complete with only 4 forces? Because I heard that some scientists they believe that there exists a 5th force, explained by something called chameleon field, that coupling with the mass. I think you have heard.
Sure. So, well. A unified theory of all the forces is what I and many others have been working on for many, many years. And eventually we will find such a theory. It might not be a field theory, probably not, because one of the forces, the force of gravity, is very hard to understand in the framework of quantum field theory, which is the quantum theory we use to explain the nuclear forces and electromagnetism. That's why string theory is so exciting, because that's a framework in which gravity and the atomic and nuclear forces fit together very nicely. Such unified theories have other forces, if you want, or other phenomena that are not just explained by the standard model. And we expect any day to discover extra phenomena that are not explained by the standard model. We haven't directly seen it yet, but we expect it. I expect that at the LHC we will discover many new particles with new forces, if you want, that we haven't yet seen. But so on the one hand, we expect from the hints we have from nature that the forces we know and understand are all unified. But we also expected that unified theory contains a lot of new stuff we haven't yet seen, and if we saw, we would call new particles, new forces. But eventually, it's all just one thing. So both will, I think, we will understand better in the next decade. The new particles, the new forces, and more hints as to how they are all unified. Maybe in a string theory framework.
Ask a question to Professor Cross. It's not about particle physics, it's about global warming. And as I am teaching thermodynamics, and I would imagine that the Earth is not really isolated system, but it's a core system, and you have this radiation from the sun. And by absorbing radiation from the sun, we emit also some radiation from the Earth. But I do not believe that the rate of radiation in and out are equal. So there will be some trap into the Earth. And I have just my personal hypothesis that all the form of hydrocarbon element, compounds are actually a picky box for the entropy. And if we have another alternative energy from destroying or cutting down the chemical bonding between H and C, we will just release the debris to the Earth, and the Earth is actually full of to change the potential energy into the form of kinetic energy. And if you just cut down all this bonding, and you create entropy to the Earth, and if you cannot release this entropy out, the avalanche temperature will increase, and this statistically will make more vibration into linear molecule where you have new disease. That's just my story, but I don't know what about your opinion.
Well, I think, I'm not sure I understood completely what you said, but we're not, we're a rather small player on the Earth. So the Earth itself is heated. Most of the Earth is this massive core made out of iron and that is totally heated and regulated by radioactivity, by radioactive elements that are decaying. And the sun plays almost no role in the temperature of the Earth. We live on a teeny little infinitesimal layer of soil on the surface, and with a very teeny little atmosphere around us. That is a very precarious element on this massive planet. And that is affected almost entirely, although eruptions can change, can affect that also on a geological timescale, by the sun. Now, the energy that comes from the sun is so much larger than all biological activity that until this growth of population and energy consumption continues for many, many thousand years, we're not going to drastically affect things the way you said, the way you were contemplating. What we're concerned about on this very delicate atmosphere is very small changes in the temperature, which are caused by basic physics of reflectivity and absorption of sunlight. Very small changes, like carbon dioxide, which is a greenhouse gas, or other greenhouse gases, can have a big effect on the temperature. But big for us is just a few degrees. This is the system of this atmospheric system is very unstable. It's very delicately balanced. We know historically has gone through large changes. What we don't know is what will happen as a consequence of what we, for the first time, are doing over a very short time. And the biggest dangers are nonlinear effects. There are others which could drive us into a new region of equilibrium that is unknown. There are other planets nearby, like Venus or Mars, which would not be so pleasant for us to live on. We live in what is a narrow region of stability. And, but we're still far away from the region where the energy that we affect directly through industry or through biological activity competes with the sun, which is a steady source of energy, free energy.
let me ask another question, if you allow. So it's about consciousness. Do you think that all the human consciousness is made from the just chemistry?
Yes.
Okay, thanks.
It's all physics. But, you know, it's, consciousness is a very interesting, so this, in neuroscience, this is the big question. What is consciousness? Can we explain consciousness? And it is an interesting, it's interesting to think about the question itself. It is only now beginning to be well-formulated question, where we can imagine how you might go about answering it and what an answer might look like. Until recently, neuroscientists rarely talked about consciousness because it was so impossible to imagine explaining consciousness. Now people are beginning to do that and probing the brain with new imaging techniques, new experimental techniques, new mapping techniques. I just received a few hours ago an email from a colleague of mine, a physicist, who has become a neuroscientist, who is one of the pioneers of a new field called the connectome, like the genome, the connectome. This new field of mapping is intending to map the brain completely. It sounds totally crazy to me. They would like to map every connection between every neuron in your brain. There are 10 to 100 billion neurons in your brain, and each of them often has connections with another 1,000 neurons. So there's something like a 10 to the 11, 10 to the 14, which is 10 to the 14 is a million, 100 million connections. And presumably, each connection is complicated because there are different neurotransmitters at each connection. So you may be another factor of 10 to 100. You have 1,000 million code plan that would constitute the map of the human brain, much as the genetic code constitutes the map of the human genome. Now, if you had that, presumably the secret of consciousness would be somewhere there. And I believe that it probably is. And we will eventually make the connection. But we're not yet at the stage where I can even imagine what an explanation would look like.
We would have the metrics, I guess.
Sorry?
We would have the metrics.
So the goal of this project is to map out. Now this has been done with very simple organisms, some worms. Every neuron and every connection is all mapped out. Interestingly enough, even in those cases, the neuroscientists still can't exactly explain how those worms function, or whether they have a consciousness.
Thank you very much.
Question. Actually, two, but I'm afraid that we run out of time. So my question is, I'm not a string theory people, so my questions will be maybe a possibility. I saw a picture you give on the screen about T quarks that all linked together. and you said it's wrong. And then when they are together, when they're trying to move apart, they create what we call the vacuum. And the vacuum, when you create a vacuum, let's say if the vacuum has a finite size and it turns out to be a classical vacuum, then some force particle will fall in. I suppose, if this vacuum has a finite size, then it admits a lower limit of the energy of the force particle to come in. Suppose there is a finite size. Then, if that is a limit, then the renormalization, will not be needed anymore. Do you think it is possible? When you create the vacuum, then instead you got
I think the vacuum is not something you create. The vacuum is as I said, it's like in this room. If you remove everything from the room, all the particles, all the people, all the air, what we call the vacuum. It is the ground state, the lowest energy state of the universe.
Yeah, but you said that is still radiation.
You remove the radiation, you turn it off, you cool this room down to close to absolute zero. You turn off all the fields. Classically, it would be totally empty. All the fields would be zero. Be turned off, be no particles, would be nothing but space and time.
So you say that's going to be a lower limit of the energy associated with the radiation.
I think it is true in the quantum vacuum, the fluctuating fields and particles in the vacuum do carry energy. And indeed, it is probably that vacuum energy that is the source of the acceleration of the universe, so-called cosmological constant, which is the energy and pressure of the vacuum.
Okay.
But that vacuum, this empty state with no particles in it, has, in quantum mechanics, dynamics, because everything in quantum mechanics has dynamics. Nothing can be at rest and non-dynamic.
And I remember the picture that you saw, the simulation,
Yes.
in the scale of the proton. What is the black area?
So in order to do that, you can't simulate the whole universe. You just consider a box in that universe. Sometimes you consider a torus, periodic boundary, a box. You should really talk about that would require an even bigger computer, bigger box, more computing. So I just, in that picture, that black area, you just had a box. The box was about the size of 10 protons. And then you looked in the middle of the box where it didn't depend too much on whether there was a box or not. But really, that vacuum extends throughout the whole universe. Vacuum is everywhere. And you should think of this as the vacuum is the medium into which particles are put or exist.
Okay. Let me ask another question.
I'm afraid that we give me the time constraint. Yes.
Okay.
You can ask Professor
Yeah, I asked
during
you
the
that.
break.
Thank you very much.
ภาษาอังกฤษจะไม่ค่อยเก่งเท่าไหร่นะครับ Can I ask you a political question? So, but when I heard that Obama received Nobel Prize, I feel that he didn't change anything. I would like to know your opinion when you heard that Obama.
Well, I I think I was as surprised as he was. You know, the Nobel Prize in Peace is given by the Norwegians. The science prizes and the literature prizes are given by the Swedes and by the Swedish Academy of Science in the case of physics, chemistry, biology. And they're chosen by scientists for scientific accomplishments, which, you know, are much easier to measure because we have a scientific what is, so it's a very well-defined thing. The Peace Prize, Nobel said the Swedes, he didn't have the Swedes give the Peace Prize. You know why that is? Because he was Swedish, but he didn't trust the Swedes. The Swedes are now a very peace-loving nation, but at the time, you know, they were a very aggressive military nation, which, for example, ruled over the Norwegians. Only about the same time that they gave up Norway to the Norwegians. And so he didn't trust the Swedes. They were too aggressive. He gave it to the Norwegians. But who chooses the Peace Prize? Do you know? It's not the Norwegian Academy of Peace. It's the Norwegian Parliament. It's chosen by politicians. It's always been a political prize, as it should be, because peace is not a scientific issue. Science is totally peaceful, or not. Nature is what it is. But peace is a political issue. The prize is awarded by politicians, and it's given to politicians. And politics is a big part of the Peace Prize. So as you know, there are theories about why did Obama get the prize. I'm sure he didn't want it because it's caused him more trouble than and he didn't want it now, maybe later. But I think my conclusion after being as surprised as you was that the Norwegian politicians were making a political decision that they would like to urge Obama to be even more peaceful. Maybe it's good if it works.
Probably that's the last question. So for the next, may I now invite the Dean of the Faculty of Science, Associate Professor Sampan Singhala to say a few words of appreciation for Professor Gross' lecture.
President Gross, Mrs. Gross, Mr. Janice Hekwine, the International Peace Foundation representative, Professor Pongsak, President of Chiang Mai University, academic colleagues, distinguished guests, ladies and gentlemen. On behalf of the Faculty of Science Chiang Mai University, may I express our sincere appreciation to Professor Gross for his marvelous and very insightful lecture today. As the President of Chiang Mai University mentioned at the outset, the visit of the Nobel laureate is very much a very special event, and we are indebted not only to Professor Gross, but also to the International Peace Foundation and the Thai Airways International for making today's event possible. As most of you may have already known, Chiang Mai University was founded 45 years ago. So 2009 was our 5th anniversary. And the Faculty of Science has organized several celebrating activities throughout last year, but today's lecture is regarded as a very special one as it concludes how we've been doing to celebrate our 5th anniversary. Professor Cross and Mrs. Cross, even though this is just a short period of time, but we really hope that you will enjoy your first visit to Chiang Mai, and certainly we will be very happy to host your future visit again, and perhaps next time around will be for a longer stay. How about the next 5 years when Chiang Mai University will reach its half-century mark? Yes, but I mention again, Professor Cross, that it was a great pleasure, and it's a great privilege for us all to listen to you talk. It's the last in a series of Nobel Laureate Science lectures. And on behalf of us all here, I would again like to thank you for fascinating insight into the very basic nature and the future of science, and the role that science will play in the future of human development. And most important of all is human survival. Thank you indeed, Professor Cross. And last but not least, may I thank all the audience for your participation and your attention during the lecture. And I do hope that you will enjoy the talk and find it beneficial and meaningful for yourselves. Thank you, everyone. Thank you.
Thank you, Associate Professor Samphan, the Dean of the Faculty of Science. Before we going out for the break and continue some of the question and discussion outside, and bring this afternoon proceeding to a close, it just remains for me to thank Professor Gross and once again for having graced this occasion with his lecture and his answer, and to wish him a happy stay for the remainder of his visit here before going to Cambodia. Also, thank you to the President, the Dean, our distinguished guests, and students, the audience for having supported this special event. This afternoon lecture will serve as an inspiration to us all, working in our various fields of science and technology to strive to achieve our highest ambitions for the benefit of our society as a whole. This now concludes today's proceeding. Thank you.